So, let us consider some problem which we want to study. Okay. And generally in quantum mechanics we start with Schrodinger equation. So, this is the Schrodinger equation, okay, very famous Schrodinger equation. So, to study any problem, we start from this Schrodinger equation, because you see we have to starting from this equation, it is like your Newton equation in classical mechanics, right. Then Maxwell equation in electricity, magnetism. Okay. So, in quantum mechanics, this is the equation. We start from this equation and then we proceed to develop the wave function for our system, okay, for our problem, whatever we want to study. What are the problem we want to study? What are the problem we want to study? So, let us say one electron or one particle, forget electron, one particle. So, it is free particle, its momentum p, it moves, okay, it moves. So, fine. So, then for this system, for this free particle, I have to develop Hamiltonian H. So, H is p square by 2m plus potential energy, okay. So, here for this system, this is 0, right, potential energy is 0, because it is free particle, there is no potential, okay. So, H is p square by 2m, and if we consider for simplicity it is linear, means one dimensional motion of this particle, free particle, one dimensional motion. So, then I can write that time I wrote something. So, H is P is basically minus I H cross, okay, del by del x, okay, and P square is minus plus, and then I square, that is minus, yes. So, that time I did mistake, I make it plus earlier. So, it will be minus H cross square by 2m, right, H cross square by 2m del 2 by del x square. Since it is one dimensional, okay, so I can write d2 by dx square, right. So, this is the my problem, Hamiltonian. So, as per my problem, or as per my system, I have to write the Hamiltonian, and then this Hamiltonian it will be put on this psi, and then I have to write this, okay. So, then what you are getting from here? Here you are getting H cross, I can write d2 psi by dx square, okay, then minus 2me by H cross square, means this side when it will come plus 2me by a cross square, okay, this psi equal to 0, okay. So this I can write say some constant 2 me by a cross square, 2 me by a cross square. So let us say some k square constant 2 me by a cross square equal to some constant I am writing, so k square. So this is your equation. This is the equation. This you know, second order differential equation. Second order differential equation is homogeneous equation. Its solution is a e to the power I k psi kx, sorry, kx, this x, yeah. So wave function will be like this, okay. So this the wave function. It's nothing but, it can also is written a1 cos kx plus a2 sin kx, okay. This way also the solution is written. So this is the this solution is called plane wave solution, okay, and it's still it's the your particle is free. So from here I have written, it's interesting to tell that E equal to, from there I can write k square a cross square by 2m, okay. And you know this is nothing but p square, you know, k square a cross square is nothing but p square, okay. So this k is basically called the momentum vector. This k is called the basically momentum vector. K is called momentum vector. Because E energy, you know, is basically p square by 2m is equivalent to p square by 2m. So k each cross is p. So that you know, probably earlier I have discussed this p equal to k each cross and E energy equal to I think omega each cross, okay. So this comes, this is the standard relation. So this momentum vector. So this way one can proceed. Now it is free particle. But it cannot go outside of a box. Okay, in a box it is free. So, but it cannot go outside the box. So then we tell in terms of potential. So at means this boundary or this face of this box, okay. So it's the barrier to the electron or to the particle. This particle cannot overcome this barrier, this wall, okay. So this is barrier. So we tell in terms of potential, this is a barrier potential. So it's a huge potential at the wall, at the surface, at the boundary of the box, okay. So then we write in terms of, so we put that condition. What condition? Okay, so there are two regions basically, this way. So this box, one dimensional box, okay, one dimensional box, okay. So here this the particle is here in this box, so it is free to move. So that means its potential is here 0, but at this position, so if it is 0 position and this is L position. So, at 0 this V is very high, this particle cannot go out. So, we tell V equal to infinity here, okay, and here V equal to infinity, here also V equal to infinity, okay. So, this way one has to model this problem like this, okay. So, this particle is free within this box, but at the surface of the box its potential is very high, it cannot go beyond this, okay. So, so you have now you have to choose psi, in such a way that it should satisfy this condition here. It is called boundary condition. One has to apply, it is in quantum mechanics, it is called boundary condition. What is the condition? So, psi is as I told. So, psi should not exist at the boundary of the box, okay. So, condition is that at when x equal to 0, x is this way, x is less than equal to 0, means this side psi has to be 0, because there is no existence of the particle in this side, there is no possibility, okay. So, psi has to be 0 and x is greater than equal to L, psi has to be equal to also 0, okay. If this partition is not there, so particle can go anywhere, everywhere one can find it. So, this solution is this, okay. This is the solution, okay. Now, if just problem, if we restrict this this particle within this box, outside it cannot go. So, then one has to put boundary condition, a realistic boundary condition, this is the boundary condition, and for this. So, this is your solution and this solution is having, you see, these are two unknown constant. Now, if you put this boundary condition, so k equal to 0, psi has to be 0, k equal to 0, psi has to be 0 means not k, x equal to 0. So, this is 1 and this is 0, okay. So, psi has to be 0, equal to 0. So, this equal to 0. So, A1 equal to 0 then, okay. So, then after this condition what I will get, psi I will get this A1 is 0. So, I will get the A2 sin kx, that is the solution, okay, A2 sin kx. Now, second one I have to apply. So, when x equal to L, psi equal to 0. So, when x equal to L, okay, that means A2 cannot be 0, this is clear, because then there will not be existence of the solution. So, A2 cannot be 0, but sin KL has to be 0, right. So, sin KL has to be 0, when it will be 0, okay. So, this KL, when KL will be 0, will be pi, will be 2 pi, will be 3 pi, will be 4 pi, then it will be 0, okay. So, that means this is giving KL equal to n pi kind of condition, n equal to 0, 1, 2, 3, right. So, so this k I can KL, so it has to follow this relation, okay. So it is giving restriction, on k value, k value. So k will be momentum vector. So it depends, so it's a now discrete value, n equal to 1, 2, 3. So we write kn equal to n pi by L, okay, n pi by L, okay, n equal to 1, 2, 3, so the k1, k2, k3, and corresponding I can write kn, okay. Now these are basically different states, it will give different states, okay, and for each state I will get momentum, I will get energy, I will get corresponding wave function psi 1, psi 2, psi 3, momentum k1, k2, k3, energy E1, E2, E3. So the system, now system wave function for the system is known to me. Now on that wave function, if I just apply different operator, I will get it's basically it will get different eigen equation, eigen value, okay, either for momentum or for energy, okay. So I will get this all information about my system, okay. So final psi will be now A2 cannot be 0, A2 is constant, okay. So one has to normalize this one, then one will get the value of A2. So psi star equal to a square basically, So I think one can find out. So within this limit it's the 1, within 0 to L one has to psi star integration 0 to L dx, psi star dx. So one can find this one. So normalized wave function for your problem you can find out, you will get the energy momentum, okay. So this way one has to proceed for different. So so one has to go one after another different kind of problem. So now our problem in atomic molecular physics, our problem, let us go there. Our problem is, what is our problem? What is our system? Our system is hydrogen like atom. Hydrogen like atom means there is a nucleus, positive charge plus JD positive charge, okay. Now so now there is a electron, now this electron is in this central, in this central field, okay, central field of nucleus, central field of nucleus. So now this electron are in this system. So in central field, a electron, central field of this of a nucleus having positive charge plus JD. Now a electron is moving in this field, in this potential, okay. So now I want to study this system, okay. I want to study this system, okay. So actually a particle, that is electron, it has negative charge. Now it is in motion in a central field, it is in motion in a central field of a nucleus, okay. So this part, now here I have to so this we will start from the Schrodinger equation. So for this I have to develop this Hamiltonian for this problem. So for this problem Hamiltonian is all the time p square by 2m kinetic energy plus potential energy. when particle was free particle, so we took it 0. Okay. When particle is in a constant field, constant potential, okay, potential is not varying with distance or time. Okay. So, then we just write as a V0. Now, in this problem, VR potential, VR is minus Z d square by R. Okay. Okay. And this potential is basically spherically symmetric potential. Spherically symmetric potential, because potential is everywhere is same on for a particular radius r. So, spherically symmetric potential, central field, we tell central field or central force. Okay. So, in our problem, this is the potential, this is the kinetic energy p square by 2m, this is the kinetic, and potential energy is this one. Okay. So, for hydrogen like problem, whatever we want to study, so here our problem is basically Z square by R. Okay. So, now we have to, so this is a Schrodinger equation, Hamiltonian is this. So, what we want to do? We want to study the system, and we want to solve this quantum mechanically, and so here what? So, I have to consider psi for this problem. Now, it is not one dimensional problem, it is the 3-dimensional problem. Okay. It is the 3-dimensional problem. So, the psi will be function of x, y, z. Okay. And say we are going to study the static, it is not dynamic one, it is not the function of, is function of time. Okay. So, we are not taking that this function of time. So, x, y, z only we are taking for stationary cases. So, this is psi, fine, but here what we saw, this potential VR, so these are, it has spherical symmetry, it has spherical symmetry. So, since it has spherical symmetry, so one has to choose proper coordinate system. You know this is the Cartesian coordinate, this is the Cartesian coordinate, this is the x, y, z, okay, Cartesian coordinate. So, coordinate system we use to fix, to locate the position of the particle. Okay. So, so for in space we need 3 coordinate. So, we have to choose coordinate system, this it is the origin, and what is x, what is y, and what is z. So, basically this along the x, and then along x amount, along the y direction y amount, and along the z direction z amount. So, this it will be x, y, z, x, y, z. Okay. So, this is the Cartesian coordinate one can use, but here since people use also this polar coordinate in 2 dimension, generally we take r phi. Okay. You remember this in 2 dimension. Okay. This point is x, y, okay, in Cartesian coordinate, but we can also fix this point defining the distance, this from origin it is r. I have to fix this one. If I just tell this distance from origin is r, then you cannot fix, because keeping the distance same, it can be any point on this circle, it can be any point on this circle, it can be any point on this circle. Okay. So, you cannot fix this one. So now if I, because aim of this of using this coordinate system to fix a point at a definitely, so it can be any point on this. Okay. Now if I define, no, it's the phi. So these distance are, and this with x axis this angle is phi, then it is now this point, it cannot move because then angle will change. Okay. So that way we fixed. So either we can use x y Cartesian coordinate, or we can use r phi in polar coordinate. Okay. Now when it is in 3 dimension, then Cartesian coordinate fine x y, then another dimension this z. But now polar coordinate, there are 2 type of coordinate are there: spherical polar coordinate and cylindrical polar coordinate. Okay. So if it has cylindrical symmetry, okay, cylindrical symmetry, so then we use cylindrical polar coordinate, or if it is spherical symmetric, then we use the spherical coordinate. Okay. So in this case, since VR is having the spherical coordinate, spherical symmetry, so we can it is convenient to use the spherical polar coordinate. So in spherical polar coordinate, you know this, what we do. So I have to fix this point. So first I can take this, okay, r, the distance is r. Now when distances are now in 3 dimension, keeping this r constant, so it will be any point on a sphere. Okay, it's not a point. So all point on the sphere is satisfy this condition. This distance is r. Okay. Now okay, then I can, to fix this point, I can define this angle with the z axis, say theta. Okay. Now it can only now, so r is fixed, now theta angle also fixed. Now what it can do? So it can be any point on this circle. Okay. So without changing r and theta, without changing with z axis, keeping theta and r fixed, so it can be any point on this circle, So that also I don't want. So I have to fix this one. So any point on this circle. So what? So if I just take projection of this on projection on the xy plane. Okay. This is the projection on the xy plane. So this height is basically, I think, yes, okay, projection on this plane, right. Now so basically as it is rotating, as I told, so you think with respect to this as a whole, this is rotating. Okay. Now if I apply angle here, say phi, so this projection, it is having angle with the x axis is phi, then now it cannot rotate. So it will have to be here. So this is the only point which we can define by r theta phi. Okay, r theta phi. Define r theta phi. Okay. So this is the spherical coordinate system. And you know this, they have relation. It's the same point, same x axis, y axis, z axis in space, origin same. Now either using r theta phi or x y z, one can define the position. Okay. And so they have relation, it's not independent. So what is then x y z? So z equal to, so z is nothing but this height, right? Its height. So this height. So if it is r, so r cos theta will be z, So this is r cos theta, and this will be r sin theta, this will be r sin theta, because this angle 90 minus theta. So, this r sin theta means this also r sin theta, fine. Now, this one, as if in 2 dimension we saw this is r and this phi, then r you can take r cos phi, this r cos phi, here r is r sin theta. So, cos phi will be x, so it is cos phi will be x, and this will be this. Okay. So, this x, this is r sin theta cos phi, x is r sin theta. So, as if this one, and then x component cos phi, and then y component along this r sin theta, it is sin phi, r sin theta sin phi. Okay. So, one can get the relation between Cartesian coordinate and the polar coordinate, right. So, now in Hamiltonian what is there? So, this in terms of kinetic energy and potential energy I have written, and in 3 dimension H is what is H? H is h cross square by 2m Laplacian for 3 dimension, right, plus its potential energy Vr. So, Vr is basically this, but just let us write Vr, and we know this is a spherical, it has spherical symmetry, and so now basically del square, we know del square, that del 2 by del x square plus del 2 by del y square by del 2 by del z square. Okay. So, in Cartesian coordinate, now this I have to find out in polar coordinate. So, it is not difficult, one has to, so we know this relation here, okay, but one has to sit and do it. So, I actually I'll tell the step, but I will avoid calculation, which so it will take time, long time. So, now I know the relation, I have to get in terms of r theta phi, and if you do that, what you will get? Laplacian, you will get del square, Laplacian you will get basically 1 by r square del by, no, I think I have to see r square del by del r, okay, r square del by del r, then here r square del by del r, okay. So, this plus 1 by r square sin theta, 1 by r square sin theta, then del by del theta sin this the sin theta del theta, sin theta del theta, okay, and then plus 1 by r square sin square theta, okay, then del 2 by del phi square, yes, del 2 by del phi square, okay. So, this is the Laplacian form, this is the in Cartesian coordinate, and this is the in spherical coordinate Laplacian. So, if Laplacian, if you know, then your Hamiltonian will be h cross square square by 2m. That means you have to multiply with h cross square by 2m, right? Okay, and then you take psi. That means you have to take psi. And then your plus Vr this psi equal to E psi. This is the Schrodinger equation in spherical polar coordinate. Okay. So, for our problem, electron is in motion. We want to study the motion of an electron in a central field of a nucleus. Okay. So, for this problem, now we have set the suitable Schrodinger equation. Okay. So, now in next class I will continue discussion on it. Thank you.